What specific problem does your method aim to solve regarding the XOR problem, and how does this contribute to understanding neural networks?
The method presented in the paper aims to solve the XOR problem using a simple artificial neural network consisting of 2 input neurons, 2 hidden neurons, and 1 output neuron. This configuration allows for a detailed analysis of the optimization process and the convergence dynamics of the network, which is crucial since the perceptron with a single hidden neuron cannot solve the XOR problem due to its insufficient capacity to memorize all cases. By studying this small network, the paper provides insights into the loss landscape's features, which impact the dynamics of backpropagation convergence, revealing the complexity of optimization processes in neural networks. Additionally, the exploration of the microcanonical entropy and its relationship to phase transitions enhances our understanding of how neural networks learn and adapt, suggesting that learning can be viewed as an annealing process through various phases in the parameter space. Ultimately, this research contributes to a deeper comprehension of the geometric properties of loss landscapes and their influence on the performance of neural networks, which is essential for developing more effective AI systems.
Can you explain step by step how your proposed neural network architecture functions to solve the XOR problem? Include the propagation of inputs through the network and the significance of activation functions used.
The proposed neural network architecture to solve the XOR problem consists of 2 input neurons, 2 hidden neurons, and 1 output neuron, making it a fully connected network with 9 parameters to optimize. Initially, the weights and biases are set to random values, and during the forward pass the inputs are processed through the network. Each input neuron sends its signal to the hidden neurons, where the activation values are calculated using the sigmoid function, which introduces nonlinearity and is well suited for binary problems. The outputs from the hidden neurons are then combined and passed to the output neuron, which also applies the sigmoid activation function to produce the final output. The significance of using the sigmoid function lies in its ability to produce outputs in a range suitable for binary classification, while ensuring that the gradients are well behaved, facilitating effective learning through backpropagation, where the network adjusts its weights and biases based on the calculated loss compared to the expected output.
Could you provide a specific example, perhaps using a truth table, to illustrate how a forward pass through your network produces output for the XOR logic?
In our study, we employed a simple artificial neural network to solve the XOR problem, which involves 2 binary inputs and 1 binary output. The truth table for the XOR logic is as follows: input 1, input 2, output 0, For a forward pass, we initialize the weights and biases randomly. For example, if we take the first case, 0, 0, the activations for each neuron are calculated using the sigmoid activation function. The input neurons receive values of 0, which propagate through the hidden layer neurons, where their activations are computed based on the weighted sums of the inputs and the biases. The output neuron then combines the activations from the hidden layer to produce the final output. If the weights and biases are optimized correctly through backpropagation, the network will output 0 for the input, 0, 0, aligning with the expected output in the truth table. This process is repeated for all 4 cases in the truth table to train the network effectively.
What advantages does your approach offer over traditional methods in solving the XOR problem, particularly in terms of loss landscape exploration and understanding convergence dynamics?
Our approach offers significant advantages over traditional methods in solving the XOR problem by focusing on a simple neural network configuration that allows for extensive exploration of the loss landscape and convergence dynamics. By utilizing a small network with only 2 hidden neurons, we can perform a large number of tests and measurements, which is impractical in larger networks. This simplicity enables us to visualize cross-sections of the loss landscape, revealing complex features such as channels, plateaus, and wells that inform the optimization process. Additionally, our analysis of convergence dynamics shows that the optimization process is influenced by the shape of the loss landscape, with distinct phases identified during training. This detailed understanding of the loss landscape and convergence behavior provides insights that can improve parameter optimization strategies, which are often overlooked in traditional approaches.
How did you validate the effectiveness of your method? Discuss the datasets used and the metrics for evaluating performance during the testing phase.
In this study, we validated the effectiveness of our method by employing a simple artificial neural network designed to solve the XOR problem, which consists of 2 input neurons, 2 hidden neurons, and 1 output neuron. The dataset used for testing included all 4 cases of the XOR truth table, allowing us to evaluate the network's performance based on its ability to produce the correct outputs for each input combination. We measured the overall performance using a total loss function that quantifies the deviation of the calculated outputs from the expected values, aiming for a loss value close to 0 to indicate successful learning. Additionally, we compared the convergence dynamics of our network under different learning rates and optimization methods, such as standard gradient descent and the atom optimizer, to assess their impact on the optimization process. The results demonstrated that the network could effectively learn the XOR logic, with the convergence of the loss function providing a clear metric for evaluating the performance during the testing phase.
Can you elaborate on the limitations or potential drawbacks of your proposed approach in relation to neural network optimization or its applicability to larger, more complex problems?
The proposed approach, while effective for analyzing a simple XOR neural network, has notable limitations when applied to larger, more complex problems. Firstly, the study focuses on a small network with only 9 parameters, which allows for exhaustive testing and detailed insights into the loss landscape. However, this simplicity does not scale well to networks with billions of neurons, where tracking the learning process becomes impractical. Additionally, the findings regarding the loss landscape and convergence dynamics may not generalize to larger networks, as the complexity of the landscape increases significantly, potentially leading to more fragmented and chaotic behavior during optimization. The paper also highlights that while larger networks can bypass entropic barriers and improve learning efficiency, the specific entropic effects observed in smaller networks may not yield the same benefits in larger configurations, where the optimization process could still be hindered by complex loss landscapes. Lastly, the study's reliance on backpropagation and specific optimization algorithms like ATOM may not adequately address the unique challenges posed by high-dimensional parameter spaces in larger networks, where alternative strategies might be necessary to ensure effective convergence.